Hello guys, good evening, and we are back with another video. And in this video, I'll be working on Thermodynamics chapter 3, which would be ideal gas. So in this video, I'll be solving about 14 practice problems, and I'll be thoroughly explaining the steps that I'm going to make and also the solutions in each practice problem. So let's start. Problem 1. Nitrogen gas at a pressure of 1.4 bars is maintained at a temperature of 27 degrees Celsius. Now, determine the specific volume in meter cube per kilogram. Let's start with number 1. Nitrogen gas. So the gas is nitrogen, and then at a pressure is 1.4 bars, and the temperature given is 27 degrees Celsius. Now the question is, the task is to find the volume. The volume, which in should be in meter cube per kilogram. Alright? We all know that the molecular weight, let's put this as big letter M, the molecular weight of nitrogen is 14. But since nitrogen is diatomic, or simply cannot stand alone, so that's why it always has two atoms whenever it is being used. So the molecular weight of nitrogen is 14, but since we have two atoms, the molecular weight becomes 14 times 2 equals 28. So we will be using 28 as our molecular weight. Now let's start with our ideal gas equation, which is pressure volume is equivalent to mass, the gas constant, times the temperature. Since mass is not specified and there's no way for us to solve for mass, what we're going to do now is we are going to factor out mass. So if we're going to factor out mass in the left side, the pressure volume, then this becomes pressure specific volume times mass is equivalent to mass, the gas constant, times its temperature. Then by dividing mass on both sides, our equation now becomes pressure specific volume equals R times time. We have our pressure, we have our temperature, and the only thing that we're going to solve for is our look for is our gas constant in order to solve for our specific volume. So let me just transform this formula in order for us to have an equation 1 to solve for our specific volume. So this will be our equation number 1. Now we are going to first solve for our gas constant, which is R. R is equivalent to, since we are basing it on the metric system, R is equivalent to 8.314 kilojoules per kilogram degree Kelvin, divided by the molecular weight, which is capital letter M, and substituting the value of our molecular weight. So our gas constant now becomes 8.314 kilojoules per kilogram degree Kelvin divided by 28. So by solving for our gas constant, simplifying our constants, 8.314 divided by 28, our gas constant for nitrogen 2 is 0.2969 kilojoules per kilogram degree Kelvin. And since we already have our R, now we can solve for our specific volume. So specific volume, basing it on our equation 1, specific volume is defined as RT all over pressure. So our R is 0.2969, then kilojoules per kilogram degree Kelvin, and multiplying it by our temperature. Our temperature is in degrees Celsius, and in using the ideal gas equation, the temperature should always be in absolute. So we need to convert 27 degrees Celsius to absolute. In metric system, the absolute temperature is in Kelvin. So we need to convert the temperature in Kelvin. So temperature is equivalent to, the conversion is degrees Celsius plus 273. So our temperature now becomes 27 plus 273, 300 degrees Celsius. So this is our absolute temperature. Now substituting this absolute temperature to our equation, this will now become 300 degree Kelvin divided by our pressure, which is in bars. And in order for us to cancel out the units, bars should be converted into either pascals or kilopascals. So we are now going to convert bars to kilopascals. So pressure is equivalent to 1.4 bars, and the conversion is 1 bar is equivalent to 1 bar here at the bottom. 1 bar is equivalent to 100 kilopascal. Now, okay, so that's for our pressure. We can now cancel this one out. Our pressure now becomes 1.4 times 100 is 140 kilopascals. Just like that. And then kilopascals can also be written as 140 kilonewton per meter squared. Now we are going to substitute this this value onto our equation number 1. So this now becomes 140 kilonewtons per meter squared. And then now we are going to cancel out units. We all know that kilojoules is the simple form of kilojoules is kilonewton meters. So we need to transform kilojoules into kilonewton meters so that we'll be able to cancel out the units. So by simplifying, we just need to multiply first the constants on our numerator. So 300 times 0.2969 we'll be able to get 89.07, and then simply canceling out degree Kelvin. So the remaining unit at our numerator will now become and also we will simplify kilojoules into kilonewton times meter divided by kilogram all over our pressure, which is 140 kilonewtons per meter squared. Now, since this is in a form of division of fractions, so meter squared will flip to the numerator and it will be multiplied to the unit of meter here at the top, and then we can cancel out newtons, kilonewtons and then our unit now becomes meter cube per kilogram. And now we need to simplify first our constant. So 89.07 divided by 140, we will have 0.6362, and then our unit will be meter cube per kilogram. So this is for our number 1. The specific volume is defined, the value for our specific volume is 0.6362 meter cube per kilogram. Alright, so that's for our problem number 1. Find the change in enthalpy of 1 kilogram of air which is heated at low pressure from 300 degrees Kelvin to 500 degrees Kelvin. We are solving now is the change in enthalpy of 1 kilogram of air which is heated at a pressure from 300 degree Kelvin to 500. So the first thing that we would do is we need to list down our given. So we have a mass of 1 kilogram, and then we have a temperature 1 which is already in absolute form, 300 degree Kelvin, and we have our temperature 2 also in absolute form, 500 degree Kelvin. That's for our and then in order to the general equation for enthalpy at constant pressure is delta H, change in enthalpy, is equivalent to M, constant specific constant pressure, specific heat, multiplied by temperature 2, the change in temperature, which is temperature 2 minus temperature 1. We already have the value for temperature 2, temperature 1, and mass, and also just to remind you, the constant pressure, specific heat for air at standard condition is in metric system is 1.0 kilojoules per kilogram degree Kelvin. And by substituting all the values, we already have our mass, constant pressure, specific heat, temperature 2 and temperature 1. All we have to do is substitute to the equation, substitute the values to our equation. So we have 1 kilogram here multiplied by our constant pressure, specific heat, which is 1.0 kilojoules per kilogram degree Kelvin, and then multiplying it by the change in our temperature, which is temperature 2 500 degree Kelvin minus temperature 1 300 degree Kelvin, and we can now solve for our change in enthalpy. So by simplifying our constants, 1 times at the numerator we have 1 times 1 times the sum 500 minus 300 all over our denominator, which is 1, and so that means our change in enthalpy is 200, and then the unit would be, we need to cancel kilograms, and then cancel Kelvin here is in kilojoules. And that's for our problem number 2. Number 3. An ideal gas has a constant pressure specific heat of 0.526 BTU per pound mass degrees Fahrenheit and a gas constant of 0.5183 kilojoules per kilogram degree Kelvin, and 15 pound mass of the gas are heated from 45 degrees Fahrenheit to 345 degrees Fahrenheit at constant volume. Determine the amount of heat transferred. Problem number 3. An ideal gas has a constant pressure specific heat of 0.526. So Cp is equivalent to 0.526 BTU per pound mass degree Fahrenheit, and the gas constant R is equivalent to 0.5183 kilojoules per kilogram degree Kelvin, and then a mass of 15 pound mass, and are heated from 45 degrees Fahrenheit, so temperature 1 equals 45 degrees Fahrenheit, and temperature 2 is equivalent to 345 degrees Fahrenheit. At a constant volume, determine the amount of heat transferred. So what we are going to solve for is our Q. The general equation for Q at a constant volume is mass, constant volume specific heat multiplied by the change in temperature. And the change of temperature needs to be in absolute form. We need to convert these temperatures into absolute form. And if you're going to look at the units, our constant pressure specific heat is in English system, our gas constant is in metric system, our mass is in English, our temperatures are in English system. So that means in order for us to be able to solve this one faster, the best thing to do is convert our gas constant into English system, so that we'll be able to solve it more efficiently. So the first thing that I would do is convert my gas constant into English system. So 0.5183 kilojoules per kilogram degree Kelvin. Now the first thing that we would do is convert. So first is I'm gonna convert my mass. So I'm gonna put 2.205 pound mass at the top and 1 kilogram at the bottom. So I can cancel out. This is reverse. Let me just correct this one. It's supposed to be 1 kilogram at the top and 2.205 pound mass at the bottom. And then the next thing that I would do is convert my Kelvin into degree Rankine. Okay, so now we will be converting our degree Kelvin into degrees Fahrenheit. In order to do so, we must first convert our degree Kelvin into degree Celsius, then degree Celsius to degree Fahrenheit, and then degree Fahrenheit to degree Rankine. So by using the concept of temperature difference, so degree Kelvin here on top, 1 degree Kelvin is equivalent to 1 degree Celsius. You might be wondering why 1 degree Kelvin is equivalent to 1 degree Celsius. This is due to the concept of temperature difference. And then what we are going to do is 5/9 degrees Celsius is equivalent to 1 degree Fahrenheit, and then this is also due to temperature difference. And then another multiplier here, converting degree Fahrenheit to degree Rankine. So 1 degree Fahrenheit is equivalent to 1 degree Rankine, just like that. So we have already converted our degree Kelvin to degree Fahrenheit. And then the next thing that we would do is convert our kilojoules to BTU. In order to do so, we must first simplify our kilojoules. Kilojoules can also be written as kilonewton meter. I'm just gonna put that here on top. I'm gonna put my open close parenthesis just like that in order to differentiate it. So I need to convert kilonewtons first into pound force. In order to do so, I must first convert my kilonewtons to newtons. So 1000 newtons all over 1 kilonewton. And then the next thing is convert my newtons to kilogram force. So 1 kilogram force, 9.81 newtons. And kilogram force to pound force. So 2.205 pound force and 1 kilogram force here at the bottom. So I have already converted my kilonewton to pound force, and now the last thing that I would do is convert my meters to the unit of foot or feet. So in order to do so, 3.28 feet is equivalent to 1 meter. Now what I need to do is cancel my units, cancel my kilojoules, cancel kilogram, cancel, and then cancel degree Kelvin, cancel degree Celsius, cancel degree Fahrenheit, cancel Newton, cancel kilonewtons, cancel kilogram force, and my remaining units would now be foot-pound force, cancel also meters, I forgot. My remaining unit would now become foot-pound force per pound mass degree Rankine. So the last step in solving for my R, converting my R, is now multiplying my constants. So 0.5183 times 5/9 all over, times 1000 times 2.205 times 3.28 divided by my denominator 2.205 times 9.81, and then we click on equals. So the resulting value would now become 103.7866. The unit would be foot-pound force per pound mass degree Rankine. This is not yet done because what we want BTU. In order to convert foot-pound force to BTU, we are going to multiply this equation by 1 BTU here at top and then 778 foot-pound force at the bottom, like that. And we can now have the final value of our R in English system, 103.78866 divided by 778. So by 778, and the answer would be 0.1237 BTU per pound mass degree Rankine. Alright. Okay, let me just go ahead and double check. So multiplying this one by this one, dividing it by our denominators. Oh, actually, it's 96.275. Alright, so let me go ahead and divide 96 divided by 778. Okay, so 0.1237 BTU per pound mass degree Rankine. That will be the final value of our R. Now, since we already have our R, we can now solve for our values. So, remaining variables. Uh, the formula for heat is mCV delta T. We have our mass given, um, change in temperature given, and we need to solve for our CV. So in order to solve for our CV, the formula for R is equivalent to Cp minus Cv. So solving for Cv, we're just gonna transpose it to the other side. So Cv now becomes Cp minus R, just like that. Now, by substituting the values, my Cp is 0.526 BTU per pound mass degree Fahrenheit, and then we need to convert degree Fahrenheit to degree Rankine, so by using the concept of temperature difference, so 1 degree Fahrenheit here, 1 degree Rankine at the bottom, and then minus our gas constant in English system, which is 1.237 BTU per pound mass degree Rankine. So we can now directly deduct this one. So Cv now becomes 0.526 minus 0.1237. So my final answer for Cv, 0.4023 BTU per pound mass degree Rankine. Now, since we already have our Cv, we can now directly solve for our Q by substituting the values of our variables. So mass is 15 pound mass. My constant volume specific heat is 0.4023 BTU per pound mass degree Rankine. And the change in temperature, since it's in degree Fahrenheit, we need to convert them by degree Celsius. So degree Rankine. So in order to do so, we are going to manually. We're not gonna do temperature difference on this one. We need to really convert them on how they are usually being converted. So I'm just gonna put it here. T1 equals 45 degree Fahrenheit. So if we are going to convert this one to Rankine, we're just gonna add 460. So 45 plus 460, 505 degree Rankine, and my temperature 2 equals 345 degrees Fahrenheit. And I'm just gonna directly add 460 to that. So 345 plus 460, so it will become 805 degree Rankine. Now, by substituting the values, 805 minus 505 degree Rankine, we need to cancel the units. Pound must cancel, Rankine cancel. We'll be left with the unit of heat, which is in BTU. Now, multiplying our constants, 15 times 0.4023 times 805 minus 505, the resulting value will be 1810.35 BTU. So that's for our problem number 3. The temperature of an ideal gas remains constant while the absolute pressure changes from 103.4 kilopascals absolute to 827.2 kilopascals absolute. Letter A. If the initial volume is 80 liters, what is the final volume? Letter B. For the 160 grams of the gas, determine the change of density expressed as a percentage of the initial density. The temperature of an ideal gas remains constant while the absolute pressure changes from, so number 4, pressure 1 is 103.4 kilopascal absolute, and then our pressure 2 is equivalent to 827.2 kilopascal absolute. And at condition A, if the initial volume is 80 liters, so volume 1 equals 80 liters, what is the final volume? So volume 2 is unknown. And at condition B, for the 160 grams of grams of gas, so mass 1 equals 160 grams. Determine the change of density expressed as a percentage of the initial density. So we are gonna solve for the change in density, percentage of the change of density, like that. And okay, so first let's solve for condition A. So I'm just gonna put it here, condition A. So every time you're solving ideal gas equations, you must first base it onto your ideal gas formula. So the ideal gas formula is pressure volume is equivalent to MRT. And then what you're going to do is you are going to determine which amongst these variables are constant. So pressure is not constant since we have two pressures. Volume is not constant since we are solving for volume 2. Since mass is not given and since the gas is the same, it's not talking about another gas, it's only talking about one ideal gas. So that means our constants are mass and our gas constant. And then another thing is, since temperature is not given, therefore temperature here is also constant. So by creating this constant, if we are going to basing the equations on these constants, therefore we can deduce that pressure 1 volume 1 is equivalent to pressure 2 volume 2, since mass, gas constant and temperature are all constants. Now by using this equation 1, we can solve directly for our volume 2 by formula transformation. So solving for volume 2 is equivalent to pressure 1 volume 1 divided by pressure 2, and just like that, or by substituting the values, pressure 2 is 827.2 kilopascal absolute. By transforming this to its simpler form, kilopascals is written as kilonewton per meter squared multiplied by our volume 1, which is 80 liters. So we need to convert this one first. And then our pressure 2 is, our pressure 1 is 103.4 kilonewton per meter squared, and our pressure 2 is 827.2 kilonewton per meter squared. And our volume is in liters. We can either solve our volume in liters or in meter cube. So let me just go ahead and convert this one into meter cube. So we have a uniformity of units that will be all in metric system. So 80 liters, the conversion would be 1000 liters here at the bottom, and then 1 meter cube at the top. So that's it, cancelling the units. So kilonewton per meter squared cancel, kilonewton per meter squared cancel, since this is in the form of division of fractions, and cancel liters. So the remaining unit will be a unit of volume in metric system, which is in meter cube. So solving for volume 2, we just simply input our constants, 103.4 times 80 all over 827.2 times 1000. Our volume 2 is 0.01 meter cube. Or if we are going to solve this one in liters, we can also convert this one to liters, back to liters. So we'll be putting 1000 liters at the top and 1 meter cube at the bottom. Cancel this one. So multiplying this, the 0.01 by 1000, that means our volume in liters is 10 liters. Now that's for condition A. Now let's go to condition B. Mass here is given as 160 grams, and our change in density is a percentage of change of density based on our density 1 is unknown. So in order to get the change in density, we first need to have our density 1 and our density 2. Let's first go for our density 1. Density 1 is equivalent to mass 1 all over volume 1. Since mass 1 is already given, 160 grams, volume 1 is already known, 80 liters, so we can directly substitute our values. So 160 grams here at the bottom and 80 liters, at the top, and 80 liters at the bottom. The resulting answer will be 160 divided by 80 equals 2. That means 2 grams per liter. This would be our density 1. And now solving for our density 2, we just need to directly input our mass. Since mass 1 is constant, so that means mass 1 is equivalent to mass 2, because we are calculating constant volume processes, so that means mass will also is always constant. Now, since mass 1 is constant, we can put here 160 grams at the top, and then our volume 2 is the one that we solved earlier, 10 liters. So this will become 160 grams divided by 10, that is 16. So 16 grams per liter. Now the thing that is being asked is the percentage of the change of density with respect to the density 1. So that means the percentage of the change of density is equivalent to change in density all over density 1 times 100%. So change in density is density 2 minus density 1. So 16 minus 2, and the unit will be grams per liter on both of them. And then our density 1 is 2 grams per liter times 100%. So the percentage of the change in density is equivalent to 16 minus 2 all over 2 times 100. It means that the percentage of the change in density is at 700%. And that's for our problem number 4. Now let's go to our